Master absolute values, also known as the modulus function for the Cambridge International A-Level Pure Mathematics 3 syllabus. Our goals today include defining the function, sketching its graphs, and solving equations and inequalities. The modulus function is a recurring theme in P3, appearing in everything from basic algebra to complex numbers and integration. It is essential for achieving an A-star because Cambridge examiners often use it to test your ability to handle multiple cases and logical conditions within a single problem. Let's start with the definition. The absolute value of a real number x, denoted by the vertical bars around x, represents its magnitude without regard to its sign. Geometrically, the modulus of x is the distance of x from the origin on a number line. Formally, we define it as a piecewise function. It is x if x is greater than or equal to 0, and negative x if x is less than 0. A key property to remember is that the modulus of x is equal to the positive square root of x squared. Squaring removes the sign, and the square root returns the magnitude. We begin with the fundamental definition. The absolute value or modulus of a real number x, written as bar x bar, represents its magnitude regardless of its sign. Geometrically, it represents the distance of a number from the origin on a number line. Because distance is never negative, the modulus is always greater than or equal to 0. Algebraically, we define it as a piecewise function. If x is positive or 0, the modulus does nothing. If x is negative, the modulus multiplies it by -1 to make it positive. A vital property to remember is that the modulus of x is equal to the positive square root of x squared. Squaring any real number removes the sign, and the positive root returns the original magnitude. This relationship is the bridge between modulus expressions and quadratic algebra. Today, we will focus on understanding and applying absolute value, a fundamental topic for your P3 examinations. To sketch a linear modulus function of the form y equals the modulus of ax plus b, we follow a systematic process that ensures accuracy for the examiner. First, sketch the line y equals ax plus b using a dashed line. This represents the function before the modulus is applied. Next, identify the x-intercept, which we call the critical point. This is where ax plus b equals 0, giving us x equals negative b over a. This point will be the vertex of our graph. The modulus function cannot have negative outputs. Therefore, we reflect the portion of the graph that lies below the x-axis into the x-axis, making it positive. The result is a distinct V-shaped graph with its vertex sitting on the x-axis at negative b over a, 0. Let's apply these steps to sketch y equals the modulus of 2x minus 4. We start by drawing the line y equals 2x minus 4 as a dashed line. It crosses the y-axis at -4 and has a gradient of 2. The x-intercept occurs where 2x minus 4 equals 0, which is at x equals 2. This is our critical point. Now, we take the part of the line below the x-axis, the segment where y is negative, and reflect it upwards. The point 0, -4 reflects to become 0, positive 4. The final result is this solid V-shaped graph. Notice that for x values greater than 2, the function is simply y equals 2x minus 4. For x values less than 2, the line has been reflected, so its equation is y equals -2x plus 4. Always label these key points and the vertex to gain full marks in your exam. Today, we are looking at the core concepts of solving modulus equations. When solving equations like the modulus of f of x equals the modulus of g of x, we have two primary techniques. The first is algebraic case analysis. Since the modulus of a equals the modulus of b implies that a must either equal b or negative b, we can split any modulus equation into two separate linear equations. The second technique is squaring both sides. We use the property that the modulus of a squared is simply a squared. This is particularly efficient in Cambridge exams when both sides of the equation contain a modulus, as it converts the equation into a standard quadratic. While both methods are valid, squaring is often the most direct route to the answer. provided you are comfortable expanding quadratics. Let's look at how both work on the same problem. Let's solve the equation modulus of 3x minus 2 equals modulus of 2x plus 7 using both methods. Using case analysis, we set the insides equal to each other or to the negative. For the first case, 3x minus 2 equals 2x plus 7. Subtracting 2x and adding 2 gives us x equals 9. For the second case, 3x minus 2 equals negative 2x minus 7. Adding 2x and adding 2 results in 5x equals negative 5. So x equals negative 1. Now, let's try squaring both sides. This gives us 3x minus 2 squared equals 2x plus 7 squared. Expanding both sides, we get 9x squared minus 12x plus 4 equals 4x squared plus 28x plus 49. Moving everything to the left, we have 5x squared minus 40x minus 45 equals 0. Dividing by 5 simplifies this to x squared minus 8x minus 9 equals 0. Factoring gives x minus 9 times x plus 1 equals 0. We find the same solutions, x equals 9 and x equals negative 1. Both methods are mathematically sound, but notice how squaring avoids the need to manually manage the negative signs in case analysis. Today we look at the concept of solving modulus inequalities. Solving inequalities requires a deep understanding of the distance interpretation. There are two standard types you must recognize. Type 1 is the modulus of x minus a is less than b. Geometrically, this means the distance between x and a is less than b. This always results in a single combined interval. Algebraically, we can write this as x is between a minus b and a plus b. Type 2 is the modulus of x minus a is greater than b. This means x is further than b units away from a. This results in two separate regions. X is less than a minus b, or x is greater than a plus b. In P3 exams, you may encounter an inequality where one side is not a constant or a modulus. If that side can be negative, squaring is dangerous because squaring an inequality only works if both sides are non-negative. In these cases, case analysis or a graphical approach is much safer. Consider the inequality 2x plus 5 is less than the modulus of x plus 1. Because the left-hand side, 2x plus 5, can be negative, we must use case analysis based on the critical point of the modulus, which is x equals negative 1. Let's visualize this. Here is the graph of y equals 2x plus 5 and y equals the modulus of x plus 1. In case 1, where x is greater than or equal to negative 1, the modulus is simply x plus 1. Solving 2x plus 5 is less than x plus 1 gives us x is less than negative 4. However, our initial condition was that x must be at least negative 1. Since no value can be both less than negative 4 and greater than negative 1, there is no solution in this region. In case 2, where x is less than negative 1, the modulus becomes negative x minus 1. Solving this, we add x to both sides to get 3x plus 5 is less than negative 1. Subtracting 5 gives 3x is less than negative 6, so x is less than negative 2. Since all values of x less than negative 2 are also less than negative 1, our condition is satisfied. Our final solution is x is less than negative 2. This shows why logic is just as important as algebra in P3. Always check your results against your initial case conditions. Let's solve a typical Cambridge P3 exam question. We are asked to solve the inequality. The modulus of 3x minus 1 is greater than the modulus of x plus 4. Since both sides of this inequality are modulus expressions, they are guaranteed to be non-negative. This means we can safely square both sides without reversing the inequality sign. Expanding the brackets, we get 9x squared minus 6x plus 1 is greater than x squared plus 8x plus 16. Subtracting the right-hand side from the left, we arrive at the quadratic inequality. 8x squared minus 14x minus 15 is greater than 0. To find the critical values, we factorize the quadratic. We are looking for factors of 8 times negative 15, which is negative 120, that add to negative 14. These are negative 20 and 6. Factoring by grouping gives us 4x plus 3 times 2x minus 5 is greater than 0. Our critical values are x equals negative 3/4 and x equals 5 over 2. Looking at the graph of this upward opening parabola, the expression is greater than 0 in the two outer regions. Therefore, our final solution is x is less than negative 0.75 or x is greater than 2.5. In the exam, always ensure you provide both regions for full marks. Let's look at 3 common errors that cost students grades in P3. The first mistake is squaring an inequality when one side is not guaranteed to be positive. For example, if you square 2x plus 5 is less than the modulus of x plus 1, you may introduce extra solutions that are actually incorrect. Always check if a side can be negative before squaring. The second error is only solving the positive case. Some students solve modulus of 3x minus 1 equals 7 by only writing 3x minus 1 equals 7. You must always include the negative case, 3x minus 1 equals negative 7, to find all possible values of x. Finally, students often confuse the and versus or logic for inequalities. Remember, a less than modulus inequality usually results in a single range, while a greater than inequality usually results in 2 separate regions. Drawing a quick sketch of the V-shaped graph can prevent this error. To finish, here are some professional tips for your Cambridge examination. Even if the question doesn't explicitly ask for a sketch, drawing the modulus graphs is the most reliable way to verify your algebraic solutions. It helps you visualize which line segments are intersecting and ensures you haven't missed a solution or included an invalid one. When sketching, Cambridge examiners look for specific features. Always label the coordinates of the vertex, which is the point on the x-axis where the expression inside the modulus is 0, and the y-intercept. Use clear, solid lines for the final modulus graph and dashed lines if you are showing the reflection process. If you use the squaring method, it only takes a few seconds to substitute your answers back into the original modulus equation. This is a foolproof way to catch expansion errors or sign mistakes before you move on to the next question. In P3 papers, a modulus inequality is often the second part of a question. If you see the word hence, look at the graph or the equation you solved in the previous part. The answer to the inequality is usually directly visible from your previous work.